All right, just a quick look at this one handout problem here. All right, so what's happening there on the back of the shaft is you're going 0.55 radians. And that's what's happening at the back of the shaft. The front of the shaft, what it has to do is it has to go down 30 degrees, which is the arctan, inverse tangent, of the 3.464 over the 6. And if you run that, you get 30 degrees, basically pretty darn close anyway. Now we want to be on the same unit system. So what you'd want to do here would be to take the 30 degrees times pi over 180. And that will get you that angle in the front in radians. And what the twist angle is the difference between the two. So if you take the 3.464 divided by 6, do an inverse tangent, you get 29.999 degrees. Multiply that by pi. And divide it by 180. That's 0.5236 radians. Okay. So what you've got in the back of the shaft, you're turning 0.5500 radians. In the front, you've got 0.5236. Okay, so you want the difference. The difference is how much the shaft can wrap up, and that's 0.0264 radians. And what that is phi. All right. So that gets you the two criteria. You've got the shear stress is 5,000 psi, so that's the maximum shear. You also have that the torsion is 32,000, right? 32,000 pound-inches. Okay, so those are the different values you've got to work with. Okay, so we good with that? Okay. All right, so now once you've got that, you know, we've got the difference there, we've got these values to work with, so now you can find the moment of inertia based on those values, and that'll get you to the radius. So what you've got for the angle is phi is TL over IG. So what that means is the torsion then will be phi IG over L. All right. And I'm sorry, we want to get actually the angle. We have the other stuff. So we solve for the, we want I sub P. And what that is G times phi, and there's phi right there, divided by, we'll get it, TL, that's TL over G times phi, okay? So what you get for this one is I sub P is 18.17, and that equals pi over 2 r to the 4. So what r equals in this case is 1.844 inches. Right. Now you've also got that the shear is TR over I. So I sub P, the moment of inertia in a polar sense, is TR over tau. All right, so what we've got phi there, we've got the torsion is 32,000 pound-inches, and we've got the maximum allowable shear is 5,000 pounds per square inch. So you can plug all that stuff in, and based on this, you can find whatever I sub P is. It is, I'm not quite sure what that comes out to be, but the R comes out to be 1.597 inches. Okay. So 1.597. That's 10.22. Those are what that is. All right. So you look at the two, you pick the bigger of the two. So there's the required radius. Now what you want to do to get the required diameter is double that. So you want to take the 1.844 inches times 2. So we got 1.844 times 2. It's 3.69 basically. You got to round to the nearest quarter inch, so that's 3.75 inches. So there's the first diameter, okay? And what you're doing there is you're running both sets of numbers, solving for the radius for both, okay? Now, if you want to know what's going on with a hollow shaft, what you want to do there is say that pi over 2 times 2 to the 4 minus the inner radius to the 4 is equal to the moment of inertia that corresponds to the value you took for the radius. Okay, so that would be 18.17. That's the value that you have to meet for your moment of inertia there, which is pi over 2 outer radius to the 4 times inner radius to the 4. So you can solve this one for R1, and that will get you 1.45. Okay. So to find the diameter, then you can take the 1.45 times 2, and that'll get you 2.90. But that's a hole that's being cut out of the center of the shaft. So which way do you round that? Up or down? Down, because you want a smaller hole. So that'd be 2.75 inches for the hole. So that's how that would work. Okay. And the hollow shaft uses the material more efficiently, you know, so those types of shapes that put the area out a long way from the axis, they're cheaper usually, or use less material. You do have to consider the fabrication costs and what you're doing. So are we doing all right with that? Just trying to go over that one. So you just, you had to kind of work your way into what that angle of twist was. It's the difference between how far the rear end of the shaft by the motor turns versus how far the front end of the shaft can turn if it's going to depress that plunger sufficiently. So you take the difference. That gets you phi. You're given the shear. We did the derivation on the torsion. Then you can put the numbers together and kind of work through and pick the bigger of the two radii. It's kind of what you want to do there. All right. All right, now the review here, I headed this out, and it looks like everyone's got a copy. Okay. So this goes back to the last midterm, Hooke's law, which converts between 2D stress and strain. Then we did the plane strain stuff, which is the biaxial strain. All right. Okay. So what we're doing with the biaxial strain is, one, we're kind of visualizing deformation. Now the deformation is what? Epsilon times L. So you could find the strain at a given angle and then find the deformation. Actually, there's a number of ways to get this. It just depends on what kind of delta you want. So maybe I'll take that out because there's a few different formulas you can use to get the deformation. Okay, you can find the strain on given elements and planes. You should know what these are and be able to visualize them. Okay. So let's say we're at some angle. What we have here for epsilon x1 is if you have your original line from there to there, the strain would represent the lengthening or shortening of the line, okay? So that would be delta, that would be L, basically, okay? Now what gamma is for a given line, gamma is the change in angle. Okay, so if this is 90 degrees and this is the new angle, what gamma is the difference between the two. So gamma equals 90 degrees minus the new angle. Okay. Now what alpha is, if you have a line at a given orientation and then some deformation occurs and the line rotates a bit, what alpha is that little angle there, okay? So essentially what there is here on this sketch is there's an alpha there and what we call beta there. What gamma is the sum of alpha and beta. So it's I think it's important to kind of understand the difference between alpha versus the shear strain. They're slightly different things. They're related, but they're not the same, okay? So to get gamma, you're starting with an angle and seeing how that angular measure changes. To get alpha, you're just looking at how a line rotates, okay? We're good? All right, so what we did with this is we calculated strains at different angles. Then we came up with sketches based on our deltas. We did it for a schematic, a rectangular plate, and a circle. We did all of those, okay? We did hoop and axial stress for pressure vessels and then found stresses and strains at different angles. Then we looked at torsion. We did shear and twist angle, non-uniform torsion, which is when you have multiple torsions applied, biaxial stress and strain, power transmission, and indeterminate torsion. Okay. Just had a few example problems that I'd handed out, and these are available online under the test downloads. This first one is just a basic one, just to apply the basic definitions of shear, which is TR over I, and then the angle, which is TL over IG. So this one's pretty straight up. You're given the torsion on the end of the shaft. You can calculate I, which would be pi over 2 R outer radius to the 4 minus inner radius to the 4. Okay, and then you can just run the numbers, TR over I and TL over IG to get the shear and the angle. Doing all right with that? Just applying those two formulas. Those are the basic things that you do analysis for when you've got a shaft. Okay. All right, so that's the first one. Second one's a little bit more involved. You've got the shaft attached to the rigid walls at point A and point C. You've got the maximum shear stress in BC is measured at 40 megapascals. Find the torsion at B, okay? All right, so what you've got then is you've got the shear stress in BC. So you've got the shear stress over on this side. Now there's a number of relationships you have to use to get this work through. The first one is that you've got the shear stress, which is TR over I. You want to back solve that for the torsion. So if you know the shear stress in BC, you can find the torsion. And what that'll be the reactive torsion at C. Now you also need to find the reactive torsion at A, because what you know is that TA plus TC is going to equal whatever TB is, okay? Because whatever that torsion in the middle will be the sum of the two reactive torsions. So you got TC, you need to work your way over here to TA. Now the way you do it is you kind of go from C to B, because you can figure out what that angle is. It's TL over IG. Okay? Now the thing is that the angle measured from C to B will also equal the angle measured from A to B. They're the same angle. They're just measured from two different points of reference. From C to B, okay, and then from A to B. So if you can find the TL over IG from C to B, that angle then will equal TL over IG from A to B. So based on that, you can find TA. Once you've got TA and TC, just add them together and get TB. That's kind of how that one goes. So that's the process, okay? So we good on that? The idea, so we're using the shear in BC to find the torsion in BC, which is the reactive torsion. Once we know the torsion in BC, we can find the angle at B, working our way from C to B, using that length. Once we know the angle at B, we realize that that's also the same angle that you would calculate going from A to B. So based on that, you can find the torsion in A, and then you just sum the two together to get the torsion in B. That's the idea. Okay. So the particulars on that, the actual calculations that you do is you find the moment of inertia, of course, pi over 2 R4. Once you know that, you can find the torsion in BC. I'm just rearranging this equation and solving it for torsion. It's tau I over R. I've got all that stuff. It's 1696 Newton meters. Once I know that, I can then find the angle measured from C to B. It comes out to be 0.06 radians. It's the torsion, which I found, times the length, divided by I, divided by G. So now I know the angle at B. Okay? Now once I know the angle at B, I realize that I could also have found it going from A to B. Okay? So if the angle is TL over IG, the torsion will be phi, the angle, times IP times G over L. I can plug all that stuff in, and I can find what the torsion is in AB that would cause that angle. It's 1526. So what I can then do is add the two torsions together, the reactive torsion at A and the one at C, and I'll get the torsion that had to be applied at B. Okay. So that's the deal with that one. We doing okay? All right, one thing on these strengths tests, of course, is the time, because there's so much calculation. Typically what I do on these tests, just so you know, is I'll give you a problem where I have you find 1 or 2 moments of inertia. And that'll be the moment of inertia for every problem, okay? So you just find it on one problem and then use it throughout the rest of the test. So you don't have to repetitively calculate the moment of inertia. Yeah?
Yeah, so about that, if the moment of inertia problem turns out to be incorrect, will that be based off of the work?
Yeah, that's so. Yeah, so the question there is if you bust the moment of inertia problem, which in about 10 years of doing this, I've had that happen 2 or 3 times. Because so just be ready for it. Be sure you can do it. But if you do it, if you're showing work, I'll just follow it through. I won't take anything more off other than that one point or two for busting something. But that always gets back to the importance of on a test. What you're doing. You're not just finding the answers. You're leaving me tracks so I can see your process. Because that way I can grade it fairly. So that is kind of a thing I want to say to everybody is, that's on you. I got to be able to follow your work and see what your process is. And if so it's no, yeah, if you bust that, I just follow your incorrect answer through. It's fine, no worries. All right. So we good on that one? All right, the next one there, we got a pressure vessel. We want to find the stress. Let's see, what do we want to do? We want to find the tensile stresses in the vessel wall in the X and Y directions. Find the tensile stress acting on plane AA. All right, so what you want to do is do the hoop and the axial. Be sure you get them going in the proper directions. The hoop splits the tank the long way. Okay, so it's a pipe. It's trying to tear a pipe in half. You think of the tank as being a pipe with just end caps on it. So the hoop tries to tear the tank in half the long way, as though the tank is a pipe or a barrel, because that's where that term comes from, is the hoops on a barrel, like go around a barrel. That's where the hoop, that word comes from. The axial tries to tear the ends off the tank. So, remember that, I'm sure that, I haven't made this test up yet, but 9 times out of 10, I put a pressure vessel problem on there, and you got to know what those mean and get them oriented properly, okay? So just be sure that, you can do that. Yeah, question?
So for stress, again, it's off the vertical, right?
What's that?
For stress.
Right, yes, and that's another thing. You're noticing I'm slipping that into the homework a lot because I want to be sure that you know that. And at some point on some test somewhere down the line, I'm going to put something in there to make sure that you know that you come off the vertical plane. I'll just tell you that because I want you to know that, okay? It's an important part of running these numbers. So just, understand that. For stress, you measure counterclockwise off the vertical plane. That's the convention for that, okay? So what I'm doing there, I'm finding the hoop and the axial. Now tau xy for a pressure vessel is 0. And then to find the tensile stress on plane AA, I run that equation. Tau xy goes to 0. Okay? And so what I'm doing here, if you'll notice, is I'm starting at the vertical plane because that's by convention is how you measure the angles for stress. So even though I gave you 20 degrees, that's not the angle you plug into the formula. You plug in the angle from the vertical plane, counterclockwise. And that's 110. 20 plus 90 more. So just remember to do that, okay? And that's one of those things you can write on the front of a test, if you got any trouble at all remembering that, just run it in your memory short term if you need to, and as soon as you get that test, just put it on the top. I mean, it's fine. That's legal. Okay. All right, real quick, why don't you sketch how that stress would act on plane AA? So we got our plane AA here. What does that stress look like? The 196,500. Which way does it go? And I'm not looking for everybody to answer it out loud. Just I want to make sure everyone understands this. So if I'm talking about the tensile stress acting on plane AA, what does that look like? That's what I'm asking. Okay. Now there's different ways you might remember this. One way is that a tensile stress is an axial stress. It's also called a normal stress, right? So that's probably the best way I can think to remember that. Well, the meaning of the word normal, it's a 3D word that means perpendicular, right? So the tensile stress, it's trying to tear that line apart. Think of just tearing it apart that way. That's what the tensile stress does. So that's the 196,500 newtons per meter squared. That's how it acts, okay? It's normal to that plane. You good with that? Okay. Good. What's that now?
The pressure on the vessel is positive.
Yeah, yeah, it's like a balloon. Yeah, it's all positive. Pressure tanks by definition are all positive tensile stress in there. I've had people ask me about submarines and the design of that, if they're the opposite of pressure vessels. I'm not quite sure it's that simple, but maybe they are. They'd all be compression, of course. And that's come up a few times in class. But yeah, they're all tension. They're pulling apart. What's the maximum normal stress in that tank wall? If you're going to design the tank wall, what do you design it for? No, I'm not talking safety factors here. What's the biggest normal stress in the tank wall? Yeah, right there. Okay. Sometimes as an engineer, I wish I had a switch in my head that would turn off the thinking too much part. Just flip that off and just keep it simple, but it's never that simple, is it? We're trained to think so much, we kind of overdo it sometimes. That's the biggest normal stress. Okay. We good with that? All right, okay. Good?
The hoop is normally bigger than the axial.
Always, yeah, the hoop is always twice the axial. It's PR over T and PR over 2T. Those are the equations. So yeah, sure. The hoop is always twice the axial. Yeah. And see, the reason, and what they do, if they build super high pressure vessels, they build them like spheres. Okay? And if you're ever down at the park in Salem, there's the Eco Globe. It's pretty cool. It's this big globe that's made into a mosaic of the earth with stuff on it. That's an old pressure vessel. That's an old mill site. They just took a pressure vessel and repurposed it as an artwork, and it's a sphere, because that way it's all axial. See, there's no hoop in a sphere. It's all axial. So you can, it's built to contain more pressure, because you don't have to worry about the hoop stress. You're just doing axial stress. All right with that? Good. All right. We want to know how long is that line going to be after those strains occur. Okay, and make sure you've got this copy. I used to have much smaller numbers in this example. I've just made them bigger so they're easier to handle it. The strain should be 0.02 and 0.05. Does everybody have that? I think if you don't, just change it and make it into that. Okay. So we want to know how much longer that line will get. So if that's what we've got the three values there, okay? So you should know what those are. That's epsilon x, epsilon y, and that's gamma xy. Is gamma xy positive or negative? Everyone just think about that for a second. Look what's happening to the angle. Okay. Yes, yeah, angle's getting bigger, isn't it? So what type of shear is that? That's negative shear, okay, which is a little unfortunate, but that's how it works. Okay, now the reason for that is, see, if you go back to stress, if you've got positive shear stress on the XY plane, your shear pattern will look like that. What that'll do is pull these corners out and push these in. So what happens is positive shear stress makes that lower left-hand angle less. That's where that comes from, okay? All right, so we just want to do this just the same way that we would, it's a biaxial problem. We're going to do it with strain. Now, unfortunately, with strain, the angle actually is from the horizontal. So the strain angle is measured from the horizontal, unlike the stress. Stress from the vertical, strain from the horizontal. Okay, so the strain comes out to be, when you run those numbers, I'm just doing the biaxial strain stuff, I'm getting, what am I getting there? I'm getting negative 0.0401. So I take 1 plus that, which actually is a minus because it's a negative number, multiply it by the original length, and I'll get 1.92 centimeters. It's going to get shorter. There's a compression acting on that. Okay. So what we're doing there is biaxial strain. Okay. Okay, what equation would I use to find the rotation of line AB after the strains are applied? Okay. So just everybody have a look. Here we got a formula sheet. Okay. Okay, it's equation 77, right? You all right with that? Oops, got a typo there. You good? You got it? Okay. So that's some biaxial strain there. All right, now the last one is just a bit on Hooke's law and some of this stress strain stuff, but it's also done in a little bit different way. Now, I don't know if I'll put this on the test or not, but I just don't want to catch you off guard if I were to. Sometimes, rather than having you run the numbers, I might just ask you, how would you do something? You know? So the way I have that is list the equations you would use to solve the problem shown, include the inputs into the equations and the output from the equations. List the equations in the order you would use them. Find the normal strain in the x direction. All right, so to get the normal strain, first thing I'm going to do, I'm going to find what nu is. Because I've given E and G, but I need nu, which is Poisson's ratio, which is a material property. I can use equation 9 to do that. I'm going to put E and G into equation 9, and I will get nu out of it. So that's the first thing I would need to do, would be to find nu. And then once I've got that, then I can use the Hooke's law first equation there, epsilon x. So 1 over E epsilon sigma x minus nu sigma y. I'm going to put in E nu sigma x and sigma y, and what I would get out of that would be epsilon x. Okay. Okay. I'm also asking how thick would the plate be after the stresses were applied. Well, what I would do, just as above, I would find nu, because I need that. Now, the thickness of the plate is in the z direction, so I would want to find epsilon z. That's equation 43. Same inputs. What I get out of it is epsilon z. All right. Then the last thing I would do, I would use this formula here, which I don't give you normally, so I just wrote that down. you just find the final thickness by taking the original thickness, which is the 2 centimeters, times 1 plus epsilon z. So there's an example. You know, I've done that in the past just because I felt like I was putting too much stuff on there and it was just too much time to do the calculations. So, we got any questions on that? Okay. All right. Let's see. Do we have any other questions generally about the test coming up? I have a look here. All right, we'll just go back. We got a couple of minutes. 221, I gave you a plate. I showed you the stresses on the plate. I wanted you to find the final dimensions of the plate. You all good on doing something like that? That's Hooke's law. And then the strain to deformation stuff. Okay, good. So let's kind of look at that. So we went through, we found epsilon x, and then the final length in the x direction using Hooke's law, and then taking the original length times 1 plus the strain. We good with that? Did the same thing in the y direction, same thing in the z direction, and then we found the angle gamma, tau xy over g. Okay, we got negative 0.0625 for the shear strain. So to find the angle, we took the original angle, which was 90, and we added the shear strain to it, which seems a little odd, but that's just how the sign conventions work. So even though it was a negative shear strain, we added it to the 90 degrees, because a negative shear strain makes the angle get bigger. Just kind of how the stuff works out for the sign convention. All right, and then I convert that to degrees. I got 93.6 degrees. So what I've got now are the final lengths and angle for that plate. I've got the shape of the plate after those loads are applied. Okay, and then we did that exercise of walking through how it would deform. I did make that one assumption there that half of the shear strain acted on line BC and half of it acted on BA. So this is 221B here that I'm looking at, that graph paper with the rectangle. So I've got a scale of 2 small boxes to the centimeter. The original, the length of BC is now 15.8 centimeters, so I'm moving that line out, or the length of the line. I'm showing that as coming out to there, because that's 0.8 centimeters out. This other one is 0.2 centimeters. So that's 0.26 centimeters. That's 0.8 centimeters. Okay. Then I have a 12 centimeter line there. So what I'm doing is I'm going to take, now to find out the final position there with the red X's, what I'm doing there is I'm looking at how those points kick out, so to speak, which is caused by the angular deformation. What I'm assuming here is that alpha is gamma over 2 and beta is gamma over 2. That was my assumption. I didn't call them alpha and beta there, but that's really what they are. Okay, I'm splitting that angle and putting half on either side. Those are the rotations of those lines. Okay, and so what I've got there is that delta on account of that rotation will be alpha times L, and delta on account of the rotation will be beta times L. That's what I'm doing there, okay? And that relies on that relationship that small angles in radians are essentially equal to the tangent of the angle, which is delta over L. Those things are all equal. So you can take an original length times an angle in radians, and you'll get the delta, the kick out one direction or the other. Okay, so that's what I'm up to there, okay? We good with that? Okay? So what I'm doing, I'm splitting the gamma in half. Now, had I given you alpha and beta, we could have calculated those. We wouldn't need those, but I'm just assuming that on this one, that half of gamma is alpha, half of gamma is beta, and I multiply those by the original lengths of the lines, and that gets me the kick out. So for C, I'm coming down 0.469, and for A, I'm going over 0.375. That's what's going on there. That's how I'm getting those final points. Okay. Good with that? You all remember that? Okay. All right. Let's see, what else do we got here? Okay, then we did this stuff. You know, you want to be able to look at a sketch. So there's a before and after sketch. You got to see that it's getting long. So I'm on problem 231. You got to read the dimension and realize the 450 with that micro symbol is a strain in the X. The 90 with the micro symbol is a strain in the Y. That's getting shorter, so that's negative. And now on this sketch, this is a schematic. So all of the strain is shown on one side so that it can be dimensioned. And that's 510. The angle's getting smaller, so that's positive. And then if you want to know what the strains will be on that element, 73 degrees with the horizontal is what's going on there. So the strain angles from the horizontal, stress angles from the vertical. Okay. Good? Okay. Then it's just a matter of running these, you know, kind of boring equations. So you just run it, biaxial strain equation for 73 degrees, you get 99. Then you run it a second time for 163 degrees, but you can also use that shortcut equation if you want, which is probably on a test be the better way to go, and get 261. And then run the shear equation for 73, and I got negative 725. So based on that, I can come up with what's going to happen to that element. And I draw a sketch. This is a schematic sketch that shows what would happen with that element. Okay. So it's going to get longer in the x1 direction at 73 degrees. It's going to get shorter 90 degrees off of that. And that lower left-hand angle, which, I don't know, maybe that's not quite the right way to say it, but it's this angle right here. The original kind of origin that's now rotated up, might be the way to say that. That's going to get bigger by 725. That micro there means 10 to the minus 6. That's what it means. For angles, it means an angle in radians. Or, I'm sorry, this is an angle in radians right there. Okay. So that's a schematic sketch that shows what's happening there. Okay. Doing all right with that? Okay. Okay, we looked at finding the deformation of a line at an angle. We went through that in our review, so that's, you know, we've done that. So that's just stress to strain with Hooke's law, strain to biaxial strain with the biaxial strain equations, and then the new length. That's what we're doing there. We also, though, had this thing that we did in class where we plotted up the shape of this circle. And to do that, we had information where we found alpha and epsilon at each of the angles there, 0, 45, 90, 135, 180, 225, 270, 315, and 315. So we went ahead and found alpha and the epsilon. What we did then was just basically create a series of lines that radiate out from the center to each one of those points. And then we just looked at how those strains would affect each one of those 8 lines going in different directions. The epsilon makes them expand out or shrink inward. The alpha rotates them. Positive counterclockwise, negative clockwise. Okay. Is that good with that one? You all good with that?
This is a stress to strain.
This one in class we did this. We went stress to strain and then strain to the biaxial strain at different angles. Okay? And we basically created a series of 8 lines radiating out from the center on that circle. And then we looked at how the strains would affect each of the 8 lines, what it would do. We took our reference as being the center of the circle. That's what we did. Right, so that stuff all kind of relates to deformations and things like that, you know. Deformations at angles, getting from stress to strain to deformation, doing that kind of stuff. That's what that first section of the material really related to. Okay. Then the rest was the pressure vessel stuff, you know, and then the torsional stuff after that. Okay, we're good with that. If you got questions tomorrow or something, you'll let me know. It's fine. This test is coming up on Thursday. And those of you online, remember, you know, if you can make arrangements with me. If you can't make it Thursday at 1 in this room, you can make arrangements with me. Okay. All right. Yep. So we'll see you all tomorrow.